All right, we're happy to have Farbod Shokrieh to speak on heights and moments of abelian varieties.
Yes, thank you. Thank you for the opportunity to speak here. Everything I talk about today is joint work with Robin de Jong. Feel free to raise your hand or interrupt me. I don't monitor chat, but hopefully the host, Shandor, will help me with that if you talk. So let me introduce the main question that I want to address. I start with okay, say number field. But you can also talk about all of this in for function field. So there is a function field. Analog that you can find in our paper. And then I have a principally polarized abelian variety. And the dimension, first of all, this is over K. I will call the dimension G. And it's perfectly fine if you want to think about elliptic curves. They're principally polarized of dimension 1. And there are two real numbers capturing the complexity, two real numbers. Capturing the complexity, geometric or arithmetic complexity of A, of this pair. The first one, due to faultings, I put a stable faultings height. It was introduced in his work on Mordell conjecture. And this doesn't even depend on the polarization. So it's just an invariant of A. I will show you how this is defined in a moment, but for now, I just want to introduce the big picture. So there is a number that was useful for arithmetic considerations. And then the second number, it's so-called Néron-Tate height of theta. So this is Néron-Tate height of theta. And what is theta? Well, lambda is a principal polarization. You can think of it as a line bundle whose global sections is one-dimensional. And you can pick a divisor representing that line bundle. And I'm going to ensure this is effective and symmetric. You can do that. There are some choices involved, but it turns out this number is not going to depend on those choices. And the main question that I want to study today is the relationship between these two numbers. There are different computations, and how are they related? And I will say what we have proved, and I will also give some history of the problem. But before doing that, let me say very quickly, I don't want to spend too much time on definition of faultings height and Néron-Tate height. Let me just say how faultings height is defined. I've prepared some notes. So you first base change to a large enough field that you will have a semi-stable reduction. This can be done. And then you look at degree of some line bundle. This degree in the number field situation should be replaced with oracle of degree. And what is this line bundle? You look at the Néron model over spec OK. K was the field. This is the ring of integers. There's a zero section you pull back the relative differentials along the zero sections. I guess there's a power of G here that I missed. So you get a line bundle. And that's a line bundle on spec OK. Well, I mean, degree doesn't make much sense, but there's a theory due to Arakelov that uses sort of infinite place to compactify the space so that the degree makes sense. So that's the notion of faulting height, stable faulting height. And the fact that I base change to a large enough field to have semi-stable reduction is responsible for the word stable. Okay, so I mean, this is mostly a reminder for people that have seen this definition, but I guess you should be able to follow my talk even if this is the first time you're seeing this definition. And then for Néron-Tate height, the second number, there is a, I imagine if you have heard of the word height, you know height of points on abelian varieties, Néron-Tate height of points, but there is a general theory due to Philippon, Gubler, Bost, Gillet, Soulet, Zhang, and among other people, that you can actually attach height to cycles, higher dimensional cycles. And this is what I'm going to do. So the definition more or less very quickly is that it's some kind of a self-intersection number. Self-intersect the line bundle associated to the principal polarization, and you restrict to the effective symmetric divisor I was talking about, and you compute some kind of a degree again. But this hat is, the reason is I'm working over a number field and I need to make sense of degree appropriately. So that's the notion of Néron-Tate height. These are different things. In particular, notice that the second number does depend on the notion of polarization. The first one, I didn't use the polarization at all. And let me just say also that Néron-Tate height has a summation formula, sort of a decomposition formula, depending on the places. This is the work of Chamberlain and Tullier plus some work of Gubler would give a formula, which I'm going to mention in my proof in a moment. But anyway, so that's the two different numbers that are kind of mysterious, and I hope you sort of followed what kind of objects they are, but you should be able to follow the talk even if you are not familiar with these definitions. Let me just make a remark that, as I mentioned, Néron-Tate height, first of all, depends on the polarization. That's clear, but has a summation formula. With local terms associated to analytic spaces or over infinite place. This is the classical analytic spaces. Over finite place, these are Berkowitz spaces. And this is due to, follows from the work of Chamberlain. Tullier. And also the work of Gubler. Okay, so that's sort of the general story that I want to study, but let me now go back and say some very concrete things. From now on, I don't have you should be able to follow everything I say, so I have no excuse. Please let me know if I go fast at any point. Moments. For this, the main player is just the lattice. And by lattice, I mean something that's isomorphic to Z to the G, a free, finitely generated free abelian group together with a product bilinear form, real valued bilinear form, which is symmetric and positive definite. That's what I mean by a lattice. And this is, so here is an example, just a Euclidean lattice. You can think of a periodic discrete set of points in the plane. Maybe I'm going to, the paper here is the ambient vector space. I'm going to use lambda r. So that's my paper, and I have a lattice. It's a periodic discrete set of points in the plane, or you could abstractly think of it as a finitely generated free abelian group with a product structure. And I'm going to introduce, so these things have a lot to do with abelian varieties. I mean, back even to Riemann, he had studied the notion of sort of analytic or complex tori, and the question of whether they're algebraic or not turned out to be related to whether certain lattices are positive definite or not, more or less. And this also come up in finite places, in the sort of when you have a non-Archimedean place. So that's why I'm going to introduce them in this generality for now. Let me define a function in this situation. I use this norm of theta notation. That should suggest there is something, this has something to do with theta functions. And what I'm going to do is something very simple. If you give me a point, I'm going to find the closest lattice point. And I'm going to find the distance to the closest lattice point. Okay, square of that distance. In this picture, if you give me a point, I don't know, here, the closest lattice point, the closest black dot is going to be here, and I'm going to record that distance squared. And for some reason, I have this weird notation, norm of theta. Right off the bat, you notice that this is a periodic function with respect to the lattice. Namely, if I, instead of this particular point, I give you a translate of that, the output is going to be the same number. In other words, this descends to the quotient. So this descends to a function which I again use the same notation on the quotient. And these objects are conveniently called tropical abelian varieties. First of all, they're G-dimensional real torus. So my lattice was G-dimensional, my vector space was G-dimensional. I'm looking at a vector space modular lattice, I get a G-dimensional real torus. And it's not just that, it does have this product structure too. So it has a quote unquote polarization, plus a polarization. You could call it like polarized real torus if you like. And these are the kind of things that you obtain if you're working over non-Archimedean fields and working with Berkovich spaces. These are sort of the essential skeleton of the associated Berkovich space. I'll say a few things about that soon. But anyway, so I have this function on this real torus. you don't need to know anything beyond that to define the following quantity. So what I call moments, I guess I will call it tropical moments. In this situation, I of this polarized real torus, it's just a real number. So you have a function, and this is a torus. It's a compact Hausdorff group. It has a Haar measure, so it makes sense. You have a function, you have a natural measure, it makes sense to integrate. And that's what I will do. Of course, Haar measure needs to be normalized. Maybe I make it probability measure. So I normalize my Haar measure so that my torus has measure 1. So this is a definition. So I've talked about in my title, I had heights and moments of abelian varieties. I've talked about heights vaguely, moments. Okay, in the case of the tropical moment, I've given a very concrete definition, and I'll talk about the Archimedean version soon. Any questions up to here? Let me maybe clarify that this number is an important number for lattices, even if you are not doing tropical geometry or number theory or algebraic geometry. Namely, you can think of this situation as a quantization problem. You're given a random point, random data, which is an analog data, and it's your discrete data are some lattice points. And what you're doing, what you can do is to quantize your data, and namely, the output would be lattice point. And then more or less the quantity that I'm defining here, so this is going to be the error in your quantization, and this is going to be the mean squared error of the quantization. What's the average error that you introduce in this quantization process? So as such, it's been actually studied extensively in other fields. Conway and Sloan have this beautiful book on sphere packing. They have an entire chapter computing these moments for root lattices. And in each case, they work quite hard. Let me just say, these are expected to be difficult to compute. And I mean that literally. I mean, on any given example, it's not easy to compute it by hand. And what I mean is that on a general lattice in a high dimension, you would expect sort of computational complexity of these problems to be difficult. I think it's expected to be sharply hard or even worse, maybe. Any questions? Right, I think I'm actually ready to. Maybe let me give one other interpretation of this, another interpretation. Which is not unfamiliar to people working with abelian varieties. There is this notion of Voronoi decomposition, which the name comes up in compactification of moduli spaces of abelian varieties. Let's define Vor0 to be the set of all points that are closest to the origin. So the distance to the origin is less than or equal to distance to any other point. Concretely, in the picture that the example I was doing, if this is origin, if you think about it, the points that are closest to the origin form a hexagon. And you can always actually go around and pick the points that are closest to any given point, and you get some kind of a decomposition, which is called Voronoi decomposition of the plane. So this is Vor 0. This gives a cell decomposition. And in fact, cell phones in the US are called cell phones because these dots can be thought of as antennas for the mobile network, and you always want to talk with the closest antenna. So in the pictures that engineers had drawn back in the day, they saw the cell picture and they called the phone cell phone. And this theory of Voronoi decompositions have application in already compactification of abelian varieties. So this is not unfamiliar to algebraic geometers. Let me just rephrase my quantity I. The tropical I can be thought of as just integrating on one of these fundamental domains, one of these hexagons, let's say Vor 0, just the distance function z. And again, I'm going to normalize Lebesgue so that Vor 0. So it makes sense to actually call it moment. It's a moment of a polytope in the sense of polyhedral geometry. You're integrating x squared function, x dot x function on your polytope. All right, I think I'm ready to give the answer and then history of the problem. Answer to the question of what is the relationship between Faltings height and the Néron-Tate height of a principally polarized abelian variety. That's theorem A. The work was done, I think it was 2018. It just got accepted, and you can find the preprint is on arXiv, but the accepted version with which many things have been improved is you can find it on my webpage, but it will be published soon as well. All right. Any questions about the moment before I write the formula? Here's the answer. Faltings height is equal to, well, twice times dimension, don't worry about that, Néron-Tate height, plus degree of the extension, again, don't worry about that. What I want to say is that the error between Faltings height and Néron-Tate height is captured by these so-called moments. So for any finite place, I'm going to have a moment term. So there is some kind of a lattice. I'll say what that lattice is attached to the, so you base change your abelian variety to your polarized abelian variety. This is not F, this is V. At that place. So think of Q as being, K as being Q. So don't worry about this term. Finite places are prime numbers. So for any prime number, you have a abelian variety over, say, QP. And as I will say, this gives you a lattice. That's what I compute the moment of. And then you have to also compute the size of the residue field. T in the case that we are working with a prime. And there is twice something for infinite places. If I was talking over function fields, I wouldn't even worry about this second term. In the case of Q, there is one extra term that comes from the place at infinity. Okay, so that's the answer. I still owe you a bunch of things. First of all, what is this number? Well, I know how to compute moments of lattices. Let me just tell you that when you have a place and abelian variety over a number field, you can look at the analytification. And that gives you an honest-to-God topological space. And the lambda that you have to work with is just the fundamental group, or first homology fundamental group. Or H1 of this honest-to-God abelian variety. And the fact that you have a polarization, that gives you a polarization or bilinear or a product structure on this H1. Okay. This bilinear form that you need on the group comes from the polarization. And here, this is actually a term that had appeared. I mean, if you are a geometer and you don't care about infinite places, you can just ignore this. But if you're a number theorist, this has this quantity had appeared before our work, and this is to say both in separate works, some of them unpublished. This quantity had appeared. Lattices, among other people. I don't know exactly the history, but you can trace it back to the work of both at least. And this is also an integral. So this is integral over the complex torus. It's much more well known that if you have a abelian variety over a, let's say, over an Archimedean field, let's say over C, then it's actually a complex torus. And so it has Haar measure again, and you can compute integrals, and it turns out there is a natural function due to faultings up to some constant. This is essentially what the quantity is. So theta, the usual sort of Riemann's theta function is has a factor of automorphy. It doesn't define a function at the level of the abelian variety itself. It's a function on the universal cover on C to the G with some factor of automorphy. You can sort of fix that factor of automorphy, and then you call the resulting thing that makes sense on the complex torus this norm of theta. And then you can look at logarithm of that and compute the integral. And that would be the Archimedean analog of what I call tropical moment. And this has a longer history. I guess our work was to bring in these tropical stuff. Okay, let me tell you how we prove this at a very sort of high level structure of the proof, but then I owe you the actual history of this problem and a relation to various interesting things that you might care about. Is the statement sort of clear? Maybe a proof structure. So as input, we take two known facts. HF, the faultings height, has a formula due to both building on earlier work of Morebai. Maybe I should also write that with relating it to local terms, relating it to local terms. We can think of that formula as some kind of a decomposition formula where for each place you get a term. And then I already mentioned Néron Tate height also as a formula. Has a summation formula relating it to local terms, but now they're local analytic terms. Local analytic terms. By analytic, I mean it relates to Berkowitz spaces. And we want to relate these two. You can imagine a natural thing to do. It's, I mean, you have to do quite a bit of work, but a natural thing is, so our contribution is to actually take the both local terms and put them in the footing of Berkowitz spaces. So express local terms of both in Berkowitz's language. Or in other words, I mean, this is along the way we were forced to actually also revisit some of the older work due to Néron and others, all sorts of formulas that you can find in Lang's book on Diophantine geometry. Many of them we could understand in the language of Berkowitz analytic spaces and bring in analysis to sort of the more classical algebraic considerations. So that's sort of the structure of the proof. The details, in fact, they were quite difficult in the version that's already on archive, but thanks to some very great suggestions by the referee, we were able to simplify some of those arguments. So if you want to look at the proof, I would suggest you look at the accepted version. But there are some things in the archive version that still might be of independent interest. So we are thinking about sort of finding an application for some of those other things. Anyway. Let me now go back and talk about the history of this problem. Of course, our work didn't appear in vacuum. What happens over, say, dimension 1, g equal to 1? You have an elliptic curve, and already the work of Faltings and a follow-up sort of exposition of that work by Silverman did give a formula for Faltings heights. Just notice that in the case of elliptic curves, this symmetric effective theta function is actually a two torsion point. The Néron Tate height of that is 0. So in our formula, this Néron Tate height should go away. So you actually have a formula directly for Faltings height. And if you compute these local terms, you actually get the Faltings and Silverman formula from that. In the case, okay, maybe I shouldn't, g equal to 1 and g equal to 2, Lattices has a paper in, I think, Compositio that solves this problem. In the case of genus 2, he sort of does a case-by-case analysis and gives these local terms without considering Berkovich spaces or moments, but somehow directly computing these things. My co-author De Jong had solved this using, so for Jacobians. But not phrased in, not in terms of moments, not in terms moments, but rather in terms of, you have a Jacobian, so you have an associated curve. Over some places, that curve might have bad reduction, then you get some combinatorial picture that can help you do some computations. And the computations were in terms of that combinatorics. But maybe more to the point, in the case of function fields, with good reduction everywhere, what happens in the formula? First of all, we are working with function fields. We don't worry about this infinite place. If you have good reduction everywhere, the lattices that you get at every place is 0. So the 0 lattice doesn't have any moment, so you don't get this either. And you get this surprising fact that Falting's height is 2g times Néron-Tate height of the theta divisor, which sounds kind of weird because Néron-Tate height does depend on the polarization. Falting's height doesn't depend on the polarization. And it's the kind of identity that should remind you of Riemann-Roch, and it is a Riemann-Roch theorem. So, so this HF is 2g times HNT. It's a well-known fact. I'm sure this was observed by someone very early on, but I don't know a good reference that this should follow from Grothendieck Riemann-Roch. Or alternatively, Morebai has this formula called key formula. So this is sort of, there are two line bundles that are isomorphic, and if you compute their degrees, they become, you get an equality like that. This is sort of the big picture. And you can suspect a Riemann-Roch type statement because something that's supposed to be complicated becomes something that doesn't. They're both complicated to me, but two different objects become the same. And finally, as I said, the Archimedean term had already appeared in earlier work. If you have back to over function fields, number fields again. With good reduction. Again, this can be traced to the work of Bost, and certainly in the work of Atissier, that Falting's height is equal to 2g Néron-Tate height plus whatever that term was. We don't have a finite place to worry about anymore. So when you have good reduction, all these sort of Berkovich space considerations are unnecessary, and this identity is proved, was proved before, and this notion of I had already appeared. So I guess you can see that our work is essentially to take advantage of places of bad reduction in the language of Berkovich spaces. And then maybe the last comment is that there are all sorts of inequalities known for Falting's height over function fields or over number fields with various degrees of sort of precision, and they many of them, or the ones that I have looked at, inequalities due to Post, Pazuki, faultings in the case of function fields, Wagoner, follow from our work, because this, for example, the second moment is bigger than or equal to 0. It was moment of a polytope. So you can take that and get an inequality out of that. Or yeah, the Néron Tate height is positive due to some Jensen inequality, and you can take that and get something out of that. Anyway, so that's the background of our work. But for the remainder of the talk, roughly 10 minutes, I would like to focus on the case of Jacobians, which some, as I advertised in the abstract, some interesting combinatorics and electrical networks come into play. So you do some electrical network computations to study heights of abelian varieties. And that's the last thing that I had planned to talk about. You have a curve, nice curve, so smooth projective connected curve over a number field or function field. And I want to study these local terms, these local contribution moments in the language of, so I want to interpret them in combinatorial terms. So first of all, you have the abelian variety I'm interested is the Jacobian, and over a place, what I care about is the analytification of that Jacobian. Remember, the lattice that I have to study is the fundamental group of that analytification. And of course, you can also analytify your curve. But it turns out in Berkovich's world, a curve has a skeleton, which is a graph. It's a metric graph. And abelian varieties in general, and in particular Jacobians, also has a skeleton, which is a real torus. And I'm going to call it Jacobian of gamma. It turns out that you can actually directly and combinatorially compute this real torus from the metric graph itself. And this is something that you can study by studying flows on this graph. All I'm saying is that if you want to study these local terms, the tropical moments, you can study them as well for this combinatorial information which comes from a graph. So the question really becomes completely about graphs and lattices attached to graphs. So question, can we compute I of Jacobian at the place V with the canonical principal polarization in terms of gamma, the metric graph, which is going to be the skeleton, let's say minimal skeleton of Berkovich space X and And the answer is really nice. So what is a metric graph? First of all, just an example. This is a metric graph. It's just like it's a geometric realization of a one-dimensional simplicial complex, but I also, every point is accessible to me. And then there is a sort of inner metric that I can encode with some numbers on these edges. So it's like a weighted graph, or they come with a number attached to them. And you can think of these numbers as being lengths of wires. So if you have a edge with 2, you can think of like 2 meters of copper wire building this line. And as such, you can think of it as electrical network or resistive electrical network. electrical network. And when you have an electrical network, you can do all sorts of Kirchhoff laws and sort of old-fashioned electrical network theory. In particular, you can talk about, for example, effective resistance. There's a function which as input takes 2 points on the graph and as output produces a real number. This is the so-called effective resistance. For example, if I want to compute the effective resistance between X and Y, I use parallel law. So if R is effective resistance between X and Y, then you remember probably 1 over R should be 1 over 2 plus 1 over 1 plus 1 over 1, and then you compute R. Let me not compute right now. I think 2/5 or something like that. 2/4. No, 2/5. Anyway. 2/5. But forgive me if I'm mistaken. Okay, so there is a effective resistance function. I promise I'm going to go back to heights. So here's a fact proved by actually some prominent arithmetic geometers. For a measure of mass 1, so total mass 1 on a metric graph, and notice I'm not saying probability measure because I'm not assuming this measure is positive. It can be negative, or it's a signed measure. You define something called energy of the measure to be a double integral. For some silly reason, there is a 1/2. Don't worry about that. You compute a double integral with kernel, which is the effective resistance function. Maybe it's worth saying, why would you look at such things? Let me say something else from electrical network world. Namely, assume you have a piece of metal, a 2-dimensional picture, and let's put electric charge of the same sign on this metal. And everybody agrees that these charges don't like each other and they repel each other and try to get away from each other, right? And in equilibrium, when things stop, like metals are supposed to be the same, you imagine that they try to maximize their mutual distances, which intuitively means they're going to go to the absolute boundary of the piece of metal. And they do it in a way that the double integral, so in the equilibrium, there is a special measure such that this whole sort of sum of mutual distances is maximized. That's the kind of thing that one studies in the notion of capacity. And that's what we are doing. So there's a capacity attached to graph with effective resistance. And so the theorem of Chinberg and Rumley and a follow-up work of Zhang can be interpreted. They don't phrase it quite the way that I'm phrasing it, but there is a unique measure which maximizes this energy. And the amount of maximum is called tau. So tau constant of a graph is the maximum of, I just said that maximum is achieved, and you can think of this as a capacity. That's the kind of thing that you would call capacity in this sort of situation of a piece of metal with electric charges. And in fact, Chinberg and Rumley were motivated by capacity theory over non-Archimedean fields and came up with this definition. But they weren't working with Berkovich spaces. They were working with dual graphs of the nodal curves at the boundary of moduli spaces. Okay, so now I can mention our theorem B. The I, the tropical moment that I want to compute, the local terms that came into my theorem A for the Faltings height computation. As I said, this is attached to the skeleton of the associated Berkovic space. So I is some quantity attached to graph, the torus that comes from the graph. So this has a formula in terms of this capacity. In particular, it's easy to compute and it's completely understood combinatorially. So L of gamma is like volume of gamma. If you have three edges, 2, 1, 1, you just add those numbers, 2 plus 1 plus 1. That's the total length or volume. And tau is just the quantity that I talked about. And this quantity can be computed, so can be computed easily. By easily, I mean in any sense that you like. There is a concrete formula you can find in another paper of mine with Robin. And also that formula is computable, meaning you can just ask a computer to compute all the quantities with a click and it will give you the number. All right, so let me end by making a couple of remarks. This identity, this is a non-Archimedean analog of a formula of an identity due to Robert Wilms. I think this was his PhD thesis on their faultings. He relates delta invariant with I invariant and phi invariant together and has some linear relation like that. And that's how we sort of conjectured this should be true. And let me end by saying more recently in 2021, my co-author and I, Robin and I, as well as Wilms independently, had this following result, that's Archimedean I is controlled by a non-Archimedean I. I should say it's asymptotics. What do I mean by that? Think of, okay, I'm going to say mostly from now on in words. Think of the moduli space of principally polarized abelian varieties. Maybe I draw a picture over so AG and look at the C points. So you have this AG. And you can probe, so you have, you can compute this quantity I, it's a real valued function on AG. There was a formula integral of some logarithm of normalized theta function. And then you can just move to the boundary. And let's pick a nice enough boundary, namely the boundary of, so let's say AG var. I don't know what the language I should use, second Voronoi. Second Voronoi compactification, and you go to the boundary and you want to see how this I behaves. And it turns out I, so the limit of I, Archimedean, is going to be, so at the boundary, you get sort of a combinatorial data coming from Voronoi decompositions, in fact. And our result can be very vaguely can be interpreted as you have it explodes, it goes to infinity, but in a nice way. So it's log some log terms. If you have a one-parameter family, let's say you're going over a one-dimensional arc, there's a parameter t, and then I non-Archimedean, and then some term of plus lower order term. Okay, so I mean, if it was a tropical talk, I would just say maybe vaguely that tropicalization or tropical limit of Archimedean I is equal to non-Archimedean I. That's a quick way of saying it. But we actually care about the error term as well. We just don't want to take the limit. Anyway, and then we have applications. Our application was compute. We give concrete formulas for the height jump of the Cereza cycle in terms of combinatorics of the boundary. And we can completely classify when this height jump is 0. So, okay, I don't want to give the definition of Cereza cycle and what I mean by height jump, but for experts, this is sort of, there's this block valence and intersection product or bilinear form that you can feed in the Cereza cycle and self-intersect and get a number, and it turns out it jumps as you go to the boundary, and we can compute that combinatorially very explicitly. And Robert gives results in the direction of uniform bounds or uniform Bogomolov type results. Yeah, so that's all I have to say. Thank you.
Okay, let's thank Farbod for a very nice talk. Any questions?
Let's see. This is Herb Clevens. This last result that you mentioned, is there any interpretation that links to the asymptotic mixed Hodge theory?
Yes. Yes, the answer is yes, and we make a mention of that in our paper. So in fact, so we do not use the asymptotics of mixed Hodge structures in our proof. What we do is, I was a concrete integral in terms of theta function, and this was a concrete integral. So the question for us is sort of do the computation. It's rather analytic computations, but let me also say, related to your, so we had in both these applications, we use Robert Wilms's identity and our identity to actually make connections with asymptotics of delta invariant and asymptotics of phi invariant and asymptotics of lambda invariant, the kind of invariants that have been introduced by Shou Zhang and others. And so we show that I goes to I is controlled by I. It was already shown by my collaborator, Robin de Jong, that delta is controlled by delta. And in his work, actually, I believe, if I recall correctly, his proof is using asymptotic Hodge theory. And somehow these two work together can give us phi goes to phi and lambda goes to lambda. So somehow implicit in our proof is this asymptotic mixed Hodge structure stuff, but our contribution didn't use that. We do actually use asymptotic Hodge theory to sort of introduce lattices and things like that in the complex situation. So, yeah, I hope it's not too vague, but you're right on.
No, thank you. It was a great talk. Thank you.
Thank you.
Right. Any other questions to Farbod? Right, then let's thank him again for this beautiful talk.